A 4 kilogram negative 20 degrees Celsius block of ice is dropped into a calorimeter that contains 12 kilograms of 10 degrees Celsius water. What is the equilibrium temperature of the system? Assume that the specific heat of ice is 2 joules per kilogram degrees Celsius. The specific heat of water is 4 joules per kilogram degrees Celsius. The latent heat of fusion of ice is 6 joules per kilogram, and the melting point of ice is 0 degrees Celsius. Okay. Whenever there's an equilibrium temperature in a system, the change in heat is equal to 0. All right. Now, whenever you have a problem like this where you have an object drop into a calorimeter and the object changes state from solid to liquid, there are 4 things you need to know, okay? In this case, the first thing is the specific heat term of ice. Heat term of ice. Second term is the latent heat term of ice. The third thing you need to know is the specific heat term of ice when it turns into water. But in this case, let's just say melted ice. And then the fourth thing you need to know is the specific heat term of water. That is already in the system. Okay, so for the specific heat terms, it goes by M, so the mass times the specific heat times the change in temperature, okay? But these are going to be personalized, taken from this. So a specific heat term of ice is going to be the mass of the ice times the specific heat of ice times the change in temperature of ice. The latent heat term of ice is just going to be the mass of ice times the latent heat of fusion of ice, which is 6, but I'm just going to write latent of ice. Specific heat term of melted ice is going to be the mass of the ice, because it's still ice, but the specific heat is going to be for water, so C sub W times the change in temperature of the melted ice. So I'm just going to write it as IW, which stands for ice to water, okay? And then for specific heat term of water, you have the mass of the water times the specific heat of water times the change in temperature of water. All right? Okay. Moving on, you want to do whatever it takes so that this is the same as this. So in order to establish that, you need to add all of these terms together and set it to 0. Okay, so you have mass of ice times specific heat of ice times change in temperature of ice plus mass of ice times latent heat plus mass of ice times specific heat of water times temperature, change in temperature of the ice that turns into water, plus mass of water times specific heat of water times change in temperature of water equals 0. Okay? Now, let's erase this to make space. All right. We have, okay, plug in what we know. We have mass of ice is 4, specific heat of ice is 2, change in temperature of ice, change in temperature is going to always be TF minus TI, okay? So we know that the final temperature is going to be 0 minus the initial temperature of ice is going to be negative 20. Okay. Added by the mass of ice, which is not 2, it is 4, times the latent heat. The latent heat of fusion of ice is 6, plus the mass of ice, which is 4, times the specific heat of water, which is 4, times temperature of ice that turned into water. So we don't know what TF is, but we know what the temperature of ice turned into water is because it's the melting point of ice, which is 0. So you have T sub F minus 0. Plus, I'm going to put this over here, the mass of water, which is 12 kg. Delete that chicken scratch. 12 kg multiplied by the specific heat of water, which is 4, multiplied by the change of temperature of water. We don't know what the final temperature of water is, but we know that the initial temperature of water is 10 degrees Celsius. So it's going to be T sub F minus 10 equals 0. Okay, now we are going to combine like terms and then solve for T sub F, because T sub F is going to be the equilibrium temperature of the system. All right, so bring out a calculator. You have 4 times 2 times 0 minus negative 20. Okay, it will be this term. Okay, so you have 160 plus 4 times 6 is 24. 24, but you want to multiply it. Oh no, you don't multiply it by anything. So you just have 24 plus 4 times 4 is 16 multiplied by T sub F minus 0 plus 12 times 4, 48 multiplied by T sub F minus 10 equals 0. Okay, now you can add 160 to 24, you should get 184. Okay, 184 plus, distribute the 16 to both terms, you get a 16 TF and 0. So it's 0, non-existent, so forget about that. You get, distribute this on both terms, you get plus 48 TF minus 48 times 10 minus 480 equals 0. Okay, now you can add 184 to a negative 480. You get a negative 296 plus 16 plus 48, 16 plus 48, 64 equals 0. Oh, no, but it will be 64 T sub F. T sub F equals 0. Add 296, right? Is that a 296? Let's see, 184 minus 480. Yeah, 296 on both sides. You have 64 T sub F equals 296 divided by 64 on both sides to solve for T sub F. Let me delete this for more space. Okay, a 296 divided by 64, you have a 4.625. So your T final is equal to 4.625 degrees Celsius. And this is the temperature where you reach equilibrium for the system.